This is problem 24 from chapter 14. It's on page 529. Bearing number 6211 from table 14.3 is carrying the set of loads in the table below, which is P1424, while rotating at 101 RPM for one 8-hour shift. Compute the expected L10 life of the bearing under these conditions if the cycle repeats continuously. If the machine operates 2 shifts per day, 6 days per week, in how many weeks would you expect to have to replace the bearing? Okay, well, you can look at the table. I'm not going to copy the, well, I guess I will copy it down because I can fill it in nicely. But let's see. Okay, so let's copy this table down to begin. So there's conditions 1, 2, and 3, and then radial loads in, let's see, these are pounds force, and they are 1750, 600, 280. Thrust loads in pounds force, and they are 350, 250, and 110. And then time in hours at 6.75 hours, 0.40 hours, and 0.85 hours. Now, what you'll notice about this is we've got really 2 problems here. We know that we're using bearing number 6211. So we can get the properties of that bearing, but what we'll have to do is combine the radial and the thrust loads. But even after we do that, we still have 3 different loading conditions. How do we calculate one overall equivalent load? Well, let's go through and let's combine all of these so that we just have one equivalent load for each condition, and then we'll combine all those conditions together. So to do this, we'll have to work through the combination process. If you go to page 516 and 517, you'll see it. But while we're at it, we may as well go to the tables and grab the information for this bearing. In 6211, let's see, where is that? 6221, 6218, here it is. Page 513, 6211, it is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's the 8th row down. And the information we'll need from here, from this bearing, is its ratings. Basically, its basic dynamic and static load ratings. So we'll have, I won't lose my place. C, the basic dynamic load rating, is 9802 pounds force. And that's for 1,000,000 revolutions, of course. And the basic static load rating is 6520 pounds force. So there are the ratings of that bearing, static and dynamic. So that's what we need from the chart. Now let's go and figure out how to combine these. And the way we'll do it is we will use equation 14.5. It looks like this. P equals VXR plus YT. Now usually when we're solving a problem where we have to size the bearing, we'll have to iterate using Y, but in our particular case, the bearing is given. And so we can actually calculate the value of Y. Now we know, before we get there, we know that the value of V is 1 because the inner race is rotating. X is always 0.56 in our book. So that's that. We've got the thrust load and the radial load, but what about Y? How do we get Y? Well, Y can be calculated based on T over C naught. So T over C naught is something we'll calculate, but notice it varies. So we've got a small problem here. Y is going to vary. Okay, so let's make another column. T over C naught, we'll calculate that value. When you do that, notice we're going to calculate the thrust load over C naught for each of these. Of course, we could do it in Excel. And you know what? Let me be consistent with my solution. I calculated T over R first, just because that's another number we need. So if you take the ratio of the thrust load to the radial load, you get these numbers: 0.2000, 0.4167, and 0.3929. So that's the thrust to radial load. Then to calculate T over C naught, here I'll have to be a little more careful because my solution that I wrote up is based on the 4th edition of the book, and the numbers for the bearings have changed a little bit. So let me just calculate these and see. So I'm going to take 350 over 6520. And that's 0.0537. Too many decimal places, but there it is. We'll do the same thing for the next. 250 over 6520. 0.0383. And then finally, the thrust load of 110 over 6520. 0.0169 or so. Now, in the past edition of the book, I got different numbers. So what I'll have to do is go and complete this without the solution. So my point is, if you're looking at the solution, the PDF copy of it, it's going to be slightly different from this. Okay. All right. So basically, what do we need to do? Well, we need to find out the value of E, because basically what this value does is it tells us, do we need to include the thrust load, or is the thrust load pretty much negligible by comparison to the radial load? Notice that in the last two cases, the thrust load is a pretty big size by comparison to the radial load, but in the first condition, even though this is the highest thrust load, it's actually not a whole lot bigger. Its percentage is nowhere near the radial load like it is in the other cases or the other conditions. So let's find the value of E for all of this. So let's see. So we need to take T over C naught and read off the value of E. So T over C naught of 0.537. Well, T over C naught in the book is 0.056. We could interpolate, but notice that it's not going to be hugely different, and it'll take me a long time on the video to perform the interpolation. So I'm just going to guesstimate E, and unless it looks like it's something I really need to interpolate. So this is pretty close to 0.056. So I'm going to take E to be 0.26 or so, okay? If I end up with a comparison that's really close, then I'll go ahead and calculate it a little bit more accurately. But I know that E is not 0.22, for example. Okay, I know E is not even close to 0.22. So that's close enough for our comparison. And then for the next line, 0.038, well, that is actually between these two, so I'll have to do some work on it. So let me just perform the interpolation quickly. So 0.056, which is the value of T over C naught in the table, less, let's see, actually what I need to do is 0.0537 less 0.028. That's the actual difference between this point and the next point down, divided by the separation distance, 0.056 less 0.028. So I've got about 92% or so, multiplied by the difference in E of 0.26 and 0.22, plus 0.22. So I get E for this one. Oh, I just interpolated this one on accident. I may as well write it down. I thought that was awfully close. So 0.57. No, the approximate. I just grabbed the wrong thing. I was trying to interpolate this one and I messed up. So let me try again. So from here, 0.0383 down to 0.028, divided by that range. The range is 0.056. Make sure I get it right. 0.056 less 0.028. Gives me 36% of the range, so 36% of 0.04, which is the distance in E from 0.22 to 0.26. Gives me that number plus 0.22. Okay, so it looks like E is 0.235 for that T over C naught. Let's interpolate on this one. Now notice this one, the 0.169 is between 0.028 and 0.014 in the T over C naught column. So let's interpolate it 0.0169 less 0.014 divided by the range 0.028 less 0.014, which is just 0.014. Okay, multiplied by the difference between 0.22 and 0.19. I can do that in my head, that's 0.03. Okay, plus 0.19 gives us 0.196 or so for E in that column. Okay, now if T over R is greater than E, that's really the question. Is T over R greater than E? Well, for this case, it's not. So we're not going to have a Y value. Basically, if T over R is greater than E, what that means is that the thrust load is a significant component of the load that's applied to the bearing. You'll notice T over R is greater here and it's greater here. So these two will have to come up with Y values, but this one, we can just neglect it. In other words, for this first row, the equivalent load P, I don't think I need anything else. Yeah, the equivalent load P there is just the radial load. So basically what happens to this equation is this part goes away because essentially Y is 0 since T over R is not greater than E. So P just goes, whoops, not to 0. It goes to the radial load. We don't use this X. Basically, in this case, it just is V times R. So that is 1750 pounds force. Okay? Now let's calculate Y for the next line. Now the 0.235, that's about 0.24. For the sake of time in this video, what I'm going to do is just calculate the value of Y halfway between. So you'll notice that Y is either 1.99 to 1.71. So I'm just going to make this quick, 1.71 divided by 2. So halfway between those two values, I'm just going to use a Y value of 1.85. That's close enough for this one. Okay, for the next, really that number ought to be just a little bit bigger because it's not 0.24, but close enough. Okay, so for the next line, I'll challenge you to calculate the actual number. That'll be a good test of your skills. For the next number, I'll perform the interpolation so you see what I get. So 0.196 is the value of E. Notice I can interpolate based on E, or I can interpolate based on T over C naught. I'm going to interpolate on E because I've already interpolated based on T over C naught. Maybe you can follow that. If not, maybe you can follow this one. So interpolating, notice E of 0.196 does not appear in the table. 0.19 does. So let's take the difference. Of course, the difference is 0.006, so 6 thousandths between this point and 0.19. Okay. That needs to be divided by the range between 0.22 and 0.19. Okay, so it's 20% of the range. And the value of Y goes from 2.3 down to 1.99. I need 20% of that difference. Now we'll have to be careful here. So 20% of 2.3 less 1.99 is 0.062, but that's going down from 2.3. So I'm going to subtract that from 2.3. When I do it, I find that Y is 2.238. I'm going to round, well, I could round that to 2.24, but I'll leave it here for your sake. Okay, so there's the value of Y for this equation for these other two loading cases. So now let's calculate the value of the equivalent load for these two loading cases. So let's see. Basically, this first part is easy. It's 56% of the radial load. So let's do that. So 56% of 600. Then I have to add to that Y, 1.85, multiplied by the thrust load of 250. Okay, so 798 and a half. Let me just round that up to 799, or really 800 pounds for the equivalent load in that condition. And then finally, doing the same thing for the last line, we'd have 56% of the radial load, 280, plus Y, which is 2.238, multiplied by the thrust load T, which is 110. Okay, so that's 403 if I round it up properly. I got 402.98. Okay, that seemed like a lot of work, and we're still not finished with the problem. Well, basically what we needed was this column, because this column tells us the equivalent radial load and gets rid of all this thrust load stuff. We don't have to worry about it anymore. Hope I haven't made a mistake so far. Like I said, I'm doing this on the board. So let's get rid of all this, because none of this really matters anymore except for this part. I don't want to erase that. So I'm trying to help you concentrate on the important part. And so that I've got some space over here, I'm going to copy this equivalent load down to 5. So 1750, 799, and 403. Now obviously setting up an Excel spreadsheet would save you some time here, so you may want to consider doing that. So there are the load conditions. Now how do I combine all of these together? Okay, well that's a different question. Let's see, look on page, find it quickly. Here we are. Page 526, equation 1410. This is not one of the equations we talked about in the slides and lecture. But here's how you calculate the equivalent load. So the mean or average of all these loads is calculated by summing up all of the individual loads to the power of P times the amount of rotation, or time if it's a constant speed, divided by the total time to the 1 over P power. Now remember that P is the same thing as the exponent. I can't remember if it was K or what we used before, but it's the same thing. So anyway, in our cases we're dealing with ball bearings, then P is equal to 3. If it's cylindrical bearings, then it's 3.33. Anyway, so all we have to do is add all this up. So now this load here, that's our P. I'm sorry the symbols changed so much. This P is not that P. Okay, unfortunately, the consistency of the letters used is not terribly good, not terribly high. But basically, this is the equivalent load, or the radial load, or whatever it is acting on the bearing, which we've got. So that's 1750 to the power of P, which is 3. Okay, notice this P is this radial load. This P is the fact that it's ball bearing. Times the number, or the life in revolutions. Now the speed of this thing is the same. It's 101 RPM, as I recall. Let's see, let's verify. Yeah, 101 RPM. Okay. So we don't have to worry about that. We can just use hours and it'll work out. If the speed was different at the various loading conditions, we'd have to actually calculate the number of revolutions. The number of revolutions at one condition and the total number of revolutions. But our life's made a little bit easier by the fact that the speed is constant. So we're summing, so we have to continue over the conditions. 799 or to the power of 3 multiplied by 0.40. I'm out of space on the video, so let me add. The next load, 403 to the third power, multiplied by 0.85. And all of this then is divided by, going for the denominator here, the sum of all these hours. Well, if you add all these up, what you find is that it's 8 hours. So just divide it by 8. And all of this then is raised to the 1/3 power. This P is the same as that P. All right, so let me plug this into my calculator and see what we get. So 1750 cubed times 6 3/4 plus 799 cubed. Oop, I made a mistake. Let me try again. 1750 to the power of 3 times 6.75 plus 799 to the power of 3 times 0.4 plus 403 to the power of 3 times 0.85 gives me the numerator here, which needs to then be divided by 8, and then raised to the 1/3 power. All right, so finally, 1,657.6 pounds force is the equivalent load that would be applied to the bearing based on all this. Notice it's not exactly this, it's a little less, but it's weighted closest to this one, which makes sense because it runs the longest at that load. So 1,657.6 pounds force is the equivalent radial load. Now we're actually done with this. Okay, so now we've got a load. Notice that this bearing is going to last longer than 10 to the 6th revolutions because this is not equal to this, right? If they were equal, we'd expect the bearing to only last 10 million revolutions. Let's find out how long it would last. Well, for that we have to use the load life equation. So let's do that next. The load life equation says that L2 over L1 equals P1 over P2. Well, now we're back to P's where we're talking about load using the symbol P. And the exponent over here, P, is different. It's the same as this K, but this P is not this P. So you'll get used to this, hopefully. It's really not too bad once you know what all these things are. But I'm going to rearrange this and solve for the life of the bearing, given that it's not running at 9802 pounds force. Okay, so L2 then is equal to the life, the standard life is 10 to the 6, a million revolutions, multiplied by P1, which is 9802 pounds force, that's the standard load on the bearing, divided by, and let me just round this to 1658 pounds force. So that's raised to the 3rd power. So let's see how long this lasts. The numbers in the text, as I said, have changed from the bearings a bit, and so this is slightly different. I'll have to switch over to my calculator. 9802 divided by 1658 to the power of 3 gives me this term. So I've got 206.6 or so times 10 to the 6th revolutions. That's how long this bearing should last. Now let's see how long that is in terms of how often we'd have to replace this thing. So then the life would be equal to 206.6 times 10 to the 6th revolutions, but we know that the bearing is run at 101 revolutions per minute. So what does this do for us? Well, it gets rid of the revolutions. It tells us how many minutes the bearing should last. Okay, now we know that there's 1 hour per 60 minutes, takes care of the minutes, and we know that one shift lasts for 8 hours. That takes care of the hours part. See, the bearing doesn't run 24 hours a day. We also know that in one day there are 2 shifts, and so the shift unit goes away, and we know that we run 1 week, 6 days. So 6 days a week is what was given in the problem statement. Okay? Make sure I've not made a mistake or the problem hasn't changed since the last edition. 2 shifts a day, 6 days a week. Yeah, and let's see, 1 hour shifts. Yeah, or 8 hour shifts, excuse me. So there's how many weeks this bearing should last. So let's see what that number is. So divide by 101, divide by 60, divide by 8, divide by 2, and divide by 6, and we get something that doesn't make sense. Let me try again. 206.6 E6 divided by 101. I may have hit a button twice or typed in a number twice. 8, 2, 6. That's better. I just hit a wrong button. 355.1 weeks or so. Now, how long is that? Well, there are 52 weeks a year, so this is 6.8 years. Now, they asked for the life in weeks, so there it is. We'd expect to have to replace this bearing almost every 7 years or so. Okay?